In this video, we're going to look at an example of finding the surface area that is represented by the intersection of two cylinders. So we've got the cylinder x squared plus z squared equals 1 and y squared plus z squared equals 1, and we want to find the area of the surface. So here's a picture of the two surfaces intersecting. Looking at just the individual pieces, here is what the shape looks like when we get those cylinders intersecting. Notice there's lots of symmetry going on. Since we've got basically the same cylinder just rotated 90 degrees from each other, we've got this side would be the same as this side, be the same as that back side, would be the same as this side over here that you can't really see in terms of surface area. So we can find the surface area of just one of these pieces and then multiply it by 4 to get the whole thing. So let's project onto the XZ plane to make things easier here. Looking at integrating over a region in the XZ plane. Mainly because if I project downward into the XY plane, I get something that lands on top of itself. If I go into the XZ plane, I just get a single projection. All right, so I can rewrite my function as y equals the square root of 1 minus z squared. Then the region that we're integrating over in the XZ plane is the disk x squared plus z squared is less than or equal to 1. So now again we can use our surface area formula here, but now we're using y as our independent variable and our x is our our y is our dependent variable, and the x and z are our independent variables in this case. We take the partial of y with respect to x, that's 0. Take the partial of y with respect to z, you get a negative 2z. When you do the chain rule, you get a negative 2z that pops out, but then you also get a 1/2, 1 minus z squared to the negative 1/2. So we just get a negative z over square root of 1 minus z squared. Now if we look at our limits, since we're going over this particular disk, we know that if we let our z limits go from negative 1 to 1, the x's have to go between negative square root of 1 minus z squared to positive square root of 1 minus z squared. And then square root of 1 over 1 minus z squared is what this will simplify to on the inside. Again, using some symmetry ideas, I can really just concentrate in the upper, if you think about this circle being drawn, just concentrate on the upper right-hand corner and then multiply it by 4. Got some nice symmetry pieces going on. So we get 4 times this integral. We notice now, though, that our limit is improper here as our z goes to 1. This is going to cause a problem down here in the denominator. So we do our usual thing with handling improper limits, is letting the limit of integration being represented by a variable and let that variable go to the improper value, if you will. So we'll do the limit as b goes to 1 from the left of that same integral, except that we've replaced the 1 with a b. This has no x's in it, so an antiderivative is just x times that function. When we put in square root of 1 minus z squared in for x, we get something that cancels and gives us 1. When we put in 0 for x, we get 0. So now we've got this integral with respect to z. That just becomes 4b. And when we do the limit, we just get 4. And then what I forgot to do is that we found remember, this was just the area of one of these sides. I forgot that at the very, very end, we need to multiply by 4. So your final answer here, even though it's not written on the slide, is I would take this particular surface area, this surface of one side, and multiply it by 4 to give us our surface that we want, or excuse me, the surface area that we want, which would be 16.